numbers. But after a long time in studying Milnor numbers in the local case, in the case of germs of functions, polynomial or map germs, I decided to study a little bit about global Milnor number, which is a number defined for polynomials, and to understand a little bit of the relationship between these two numbers and what can we do with them. First, I am going to talk a little bit about the Milnor-Lie fibration, which is very common. Everybody knows the Milnor fibration here is the fiber on a ball. And if we consider this function Z2 plus W3 less, easier, but it goes from C0 to C. I am looking for the germ of this function by now. If we consider f minus 1 of 0, you have something like that. And if you look to f minus 1 of C, for C is small enough, you have something like that. And in fact, the fibration that I'm talking about is given by these points in the ball. Okay? This is the very well-known Milnor fibration. I will not talk too much about it, but I want to go to the Milnor number. If f has an isolated singularity in the origin, the Milnor number is the number of spheres on this bouquet. This is a multiple type of a bouquet. The fiber is already the 2 points in that picture. And we can compute this Milnor number. There are several ways to compute it. You know much better than me. But in algebraic way is the complex dimension of this algebra. On plus 1 is the ring of holomorphic germs at origin. And GF is the Jacobian ideal, the ideal generated by the partial derivatives of the germ. So we forget about the geometry and go to algebra. And we also go from the local to the global. Now I am considering a function in the complex polynomials ring C0Zn with a finite number of singular points. So we can define the Milnor number, the global Milnor number, as the Milnor number at infinity, as the sum of the local Milnor numbers for each isolated singularity of the polynomial f. If it has a finite number of isolated singularities, we have the local Milnor number. We can consider all isolated singularities. Just sum them to get this number. In fact, we have an algebraic way to compute it, and from this algebraic way, we can easily deduce that we are looking to the Jacobian ideal in this ring of polynomials, computing the multiplicity, and we have this multiplicity as the sum of these multiplicities. Okay? This result comes from this sum. What can I say about Milnor number if I don't use Newton polyhedron? This is essential in my work. And we can see in the local singularity theory several works to computing the Milnor number of isolated singularities. Fukui, Damon Gaffney, Fukui, Yoshinaga, Kushnirenko, Oka, Wall. There are much others, but these are the main reference. But the most interesting in my point of view for these computations that I'm doing is given by Kushnirenko. And he showed the formula to compute the Mueller number. I'm going to show it later, which isolated the singularity of a function, germ function, which is Newton non-degenerate at the origin using the Newton polyhedron of the germ. Moreover, in the same article of Kushnirenko, he considers three cases: the germs, the case of polynomials, and the case of Lorentz series. I am talking just in the polynomials and germs case. And Kushnirenko shows that you can also compute the global Mueller number for complex polynomials with a finite number of singularity, just considering the condition that it's Newton non-degenerate. Two Newton non-degenerate conditions. This is at origin. This is at infinity. I'm going to explain the difference between them later. And from this difference, we can see several things which are interesting in my opinion. Local Newton polyhedron. A Newton polyhedron is nothing else than a convex hull. If you consider a set of points, you can take convex hull. First, for the local Newton polyhedron, we are not just considering convex hull of points, but the convex hull of sets. In this case, just to show what's going on, we are in R2, we are considering 3 points, 4 points, 2, 0, 0, 3, 1, 1, and 2, 3. The first Newton polyhedron that I'm considering is the local Newton polyhedron. You take this point, this, then you take 1, 1, and the other one is 2, 3, 2, this one, okay? To compute the Newton polyhedron of this set, we look to this set, we look to this set, we look to this set, then we take the convex hull. This is gamma plus of A. It's important to emphasize that in this example, we have another polygon here, which I call gamma minus of A, which is the difference between R2 plus, because I'm looking for polygons. By now, it's just points, but this set is also important in the calculation, okay? If you can do it for any set of points, we can define the Newton polyhedron of a germ, just looking for the exponents which appear in the Taylor series of the germ, okay? The germ has a Taylor series, aka different to 0, so we are looking for the k like this. If we have here another definition, the germ is convenient or commode in Kushnirenko's notation or fit in Damon-Gaffney notation if the exponents meet the coordinate axis. And just to show something, we can look to the germ f xy, x2 plus y3 plus xy plus x2 y3 gives us already the same Newton polyhedron given by the set A. So when you think about the set A, we can just consider the set of exponents with monomials that we are looking, okay? I have two examples of convenient germs. The convenient is to fix here. The other one is not convenient because there is no pure term in the variable y, okay? But can be with isolated singularity. I will restrict my talk just on convenient germs, just to become it easier to understand, not because it's a problem, the other, but it's easier to look at them. Now we go to the global Newton polyhedron. The global Newton polyhedron is a little bit different, but it's done in quite the same way. We need to have a finite subset A, like the other. But when we do the other, we consider K plus V. This is why I wrote these sets to take the convex rule, okay? But here we do a different way. We just look at the set of points and add the point of the origin. The same set, I have the origin here, I have 2 O here, I have O3, 1, 1, and we have 2, 3 here, okay? If I consider the convex rule of this set, I have this, the union with the origin gives me this set. The main difference here, we need to understand what's going on in the origin. Okay, so we need to look what's going from down to up. If you are looking to the global Newton polyhedron, you want to control what's going out because you want to control the terms which are going to infinite. So you need to control things that's coming from the infinite to the origin. Okay? It's very different, the Newton polyhedron, for this case and for that case. Okay? We have, obviously, they must be different after some calculations. This is the first one, goes up. The second one is just this. Okay? Why? And for not more germs, okay, I am considering polynomials, not germs of polynomials in the global case now. I just consider the Newton polyhedron as the Newton polyhedron of the support of all exponents which appear in the polynomial, okay? In this situation, I'm looking to a germ in ON. So it's a Taylor series of a function. Here, I am considering a polynomial. Okay? G is a polynomial in the set of polynomials. To compute the Milnor numbers using Newton polyhedron, we need to know the Newton homogeneity condition, which is quite very well known in the local case. For the global case, the situation is the same. The only difference is that we need to look to different Newton polyhedron. There we have the big one, the global Newton polyhedron. Here we have a small one, which is the local Newton polyhedron. Okay? We say that the germ for the local case is non-degenerate if we can restrict the germ to the compact face, okay, and have a finite codimension ideal in the cones. In fact, this is a purely algebraic definition, and there is a geometric way to compute this also, which I'm going to show in the next definition. But moreover, if we have n germ with isolated singularity at the origin, we can consider the condition that F is Newton non-degenerate to compute the Müller number for the germ, looking for the Newton number. The Newton number is given as this alternate sum. Okay? Vn is the volume of the big polyhedron that we have. The other ones are the smaller volume that we have to intercept with the coordinate axis, and we go down, 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 and we have an alternate sum. In the two-dimensional case, the number nu zero of F is always 2 times A less A plus B. Here I have A 0. Here I have 0B. If we have a convenient germ, we always have these numbers well defined, the first which appear in the Taylor series. So this is this number plus this, and this is 2 times this area. This is, in fact, 2 factorial. Okay? Oh, close one, sorry. I forgot. Yes, plus 1, thank you. This is the result of Kuchnirenko. This is the main result of Kuchnirenko for the local case. And so we have an inequality always, and the equality if the germ is Newton non-degenerate. Now we go to the polynomial case. We consider now the Newton polyhedron, the global Newton polyhedron of the germ, the big one. Okay? We restrict the generator GI, as I showed before, where here, the same notation is gxi dj dxi, the derivative multiplied by the same coordinate, okay? In this situation, this is the same GI here. Restricted to the compact faces, the zero set of these polynomials is contained in this set, okay? This is quite an analogous definition than this, okay? But here I put in the algebraic way and here in the geometric way. The most important is that for polynomial functions, any polynomial function with a finite number of singular points, okay? Then we have the Müller number of F always smaller or bigger than the Newton number. The Newton number is defined in an analogous way than the other, but the main difference is not now. We have the Müller number of infinity of the polynomial F. This is the big A, okay? The coordinates B and A are the same. One is the same, but here, let's call it A0, and we have the area A infinity here. Two different numbers because you have two different Newton polyhedron, only because of this. The definition is the same of the Newton number. I used the index infinity and 0 just to differentiate from the local to the global, okay? This is the most important thing that you need to realize. Okay. Sorry? Sorry. Kuchnirenko. Oh, they are all in Kuchnirenko's paper. Okay? The main difference is that, for the first result, for the local case, we need only the area of the local Newton polyhedron, and for the other one, we need the area of the big Newton polyhedron. And the inequalities are different. This is smaller than this, and the other side, the equality is different. The Milnor number at infinity goes down, okay? This is the same thing that I was telling before. When you look at the local case, you need to control what's going down the Newton polyhedron. You need to control here. If you consider there is nothing else here, because this is the principal part of the germ, looking for the local case. So if you have the Newton non-degeneracy condition here, it doesn't matter what we have up. The Milnor number is given only by this. Okay? If you are in the other situation, you need to control what's going up. So you take all the monomials which give you the bigger Newton polyhedron, and if this is Newton non-degenerate, doesn't matter what you include here, including this 0.11, but the global Milnor number doesn't change, okay, in the non-degenerate case. This is general result for polynomial with finite number of singular points. Now I'm going to quasi-homogeneous functions. This is the most interesting, in my opinion, to check these two results. We say that a germ is a function. Doesn't matter if it's germ or polynomial or what is. It's quasi-homogeneous or weighted homogeneous. This is quite the traditional way to define it. Of type R0, Rn, D. If there are integers R0, Rn, the weights, and an integer D. Can be rational numbers also, doesn't matter. You can do it. But what is important is this equality. This is like you, homogenizing this function, but doing different weights for the variables, okay? For example, we have the Z2 plus W3, as I told you before. This is quasi-homogeneous of type 2, 3, and 6. Oh, it's wrong. Sorry. This is 2, so I need to put 3 here, 2 here, and 6. If I look to the variables ZW, it's wrong. You have to change it, sorry. Okay? And this is also quasi-homogeneous of the same type, 3, 2. It's wrong here also. But this is not with isolated singularity because it's non-reduced quasi-homogeneous function. But doesn't matter. The quasi-homogeneous is not a condition to be with isolated singularity or not, okay? And both are convenient because both Newton polyhedron encounter the coordinate axis. This is the main property which I want to tell you about these quasi-homogeneous maps. First, the Newton polyhedron in the local case is the same than the Newton polyhedron in the global case. This is very, very funny in my opinion, and it's the most important property for this kind of polynomials. It's just a question of analytic geometry. If you have a convenient and quasi homogeneous polynomial, you have all coordinate axes being meeting by some monomials, and you have all monomials belonging to one hyperplane. Okay? So, both gamma plus gamma infinity of f and gamma 0 of f are equal. In fact, here I should put gamma less of f, which is the down. Trivial. Okay? Moreover, we have both Newton numbers the same. It's the same Newton polarhedron. See if it's the same Newton polarhedron. The Newton number only depends on the Newton polarhedron. From this result, the first consequence, both Milnor numbers are equal. Why? Because if the polynomial is convenient, quasi-homogeneous, and with isolated singularity, it is Newton non-degenerate. So if it is Newton non-degenerate, we just apply the result of Coutinho-Renko to show that this number is equal to this is equal to this, and this is equal to this. So we have this equality. Which conclusion we can have from this equality? It has only one isolated singularity at 0. Why? Because this is the sum of all Milnor numbers, local Milnor numbers. If they are the same, there is just one Milnor number, because these numbers are integers. So there is just one isolated singularity for any polynomial function which is quasi-homogeneous with isolated singularities. This is the most interesting. And I believe that you can find this proof in different ways. But using Newton polarhedron, I have never seen it before. Moreover, the Milnor radius. What's the Milnor radius? The Milnor radius is the biggest size of the ball that we have in the Milnor, that we can guarantee that's a Milnor vibration. So if we have only one isolated singularity, to do the Milnor vibration doesn't matter the radius, because the problem to compute the Milnor radius is if you have more than one. If you have only one, doesn't matter, you have always the same situation. Okay? So you can go to infinite with this number, just using Newton polarhedron to get a very, very important topological result. You don't need to know nothing about the topology to conclude this. Just to compute Newton polarhedron. Just to see if you have one isolated singularity here, another isolated singularity here, okay, we can compute the Milnor radius. This is not the case of quasi-homogeneous, okay? If you have two isolated singularities, it's not quasi-homogeneous anymore. We know from these results. When you go up with the radius, sometimes they will match. So you need to go down. This is why the Milnor result is only a local result, not a global. Because if you have more than one isolated singularity, you cannot put the radius to infinity. You have to restrict the local neighborhood of each isolated singularity to compute. Okay? This is already the main properties which I understand, that from Newton polarhedron you can find some very topological and geometrical results for at least quasi-homogeneous. Okay? The question now is a little bit different. It is about the constancy of Milnor numbers in families. This is a very classical question in local singularity theory, and it's well known from all the articles that I told you before, that if the function is semi-quasi-homogeneous, to be semi-quasi-homogeneous means that you have a function which is quasi-homogeneous with isolated singularity, and then you add as many monomials as you want, but with weight degree strictly bigger than the first weight degree that you fixed. The main condition for it to be semi-quasi-homogeneous, this has isolated singularity, okay? I am still considering convenient isolated singularity just for simplicity. But for the semi-quasi-homogeneous, it's well known. This is a kind of function that's semi-quasi-homogeneous. Just add one term of higher order. And from the works of Vainsencher, Kochinirenko, Damon Gaffney, or Yoshinaga, if you consider convenient quasi-homogeneous germ, F0, okay, with isolated singularity, okay? So if you consider deformations of this germ, this is with isolated singularity. I needed to write it here, but I forgot, sorry. And these are quasi-homogeneous, but with higher homogeneous degree than the first one, so you have the constants of the Milnor number. For the topology, this is very, very important. In the local case, the Milnor number controls the topology in families, okay? And what happens if we go to the polynomial case? This is funny. I found this a little bit time ago. I've been working with the pre-quasi-homogeneous germ a long time because I wanted to understand the local case, which Milnor constant deformations we can have. And for free, just applying the result of Kochinirenko, we have something very interesting, in my opinion. We consider not more monomials to form a Taylor series, but just polynomial. Adding, we have the quasi-homogeneous part with isolated singularity. We add the monomials, which are inside the Newton polyhedron, the global Newton polyhedron. If we do this, we have, from the work of Kochinirenko, if F0 is convenient, quasi-homogeneous polynomial with isolated singularity, and each polynomial here is polynomial, there's only a finite number of monomials inside this Newton polyhedron, is quasi-homogeneous, but with weight degree smaller than, then we also have the constants of the Milnor number, but the global Milnor number. Okay? So the pre-quasi-homogeneous germs, which were introduced a long time ago by myself to study topological triviality in the local case, they play the similar, let's say they are the similar functions then when we look to the Milnor constant deformations of quasi-homogeneous polynomials. So I will stop now. Thank you very much.